and welcome, and thank you for joining me here today. Right, we'll just give a couple of seconds. Okay. The clicker hopefully works. Cool. So, to kick things off, my name is Chris Nesbitt-Smith. I'm based in London and currently work with some well-known brands like Learn-K, Scrollplane, and various bits of kind of UK government. I'm also a tinkerer of open source stuff. I've been abusing Kubernetes in production since it was 0.4. So believe me when I say it's been a journey. I've definitely got the whirlwinds to show for it. We'll have plenty of time for questions and your best heckles at the end. But if we run out of time, or you're not watching this in real time, of course, then please do find me on LinkedIn or, of course, in the Linode Slack. I believe we've got some a channel set up there. I'll try and keep an eye on the comments on the chat too. Okay, so Kubernetes embraces the idea of treating your servers as a single unit and abstracts away how individual computer resources operate. So from a collection of 3 servers, Kubernetes will make, in effect, a single cluster that behaves like one. So if we imagine having our 3 servers, you can use one of those servers to install the Kubernetes control plane. The remaining servers can join the cluster as worker nodes. Once the setup is complete, the servers are abstracted from you, and you can deal with Kubernetes as a single unit. When you want to deploy a container, you submit your request to the cluster, and Kubernetes takes care of executing, say, Docker run and scheduling the container in the right server. The same happens for all the other containers. So for every deployment, Kubernetes finds the best place in order to run your application. Kubernetes can automatically scale your application for you too. But you'll likely find that you run out of compute resource. But all is not lost. Kubernetes has yet another trick up its sleeve. Given access to your underlying infrastructure when you run out, it can dynamically provision additional compute when you require it using the cluster autoscaler. If you didn't see Salman's fantastic talk on this a couple of weeks ago, I highly recommend watching that back for a really insightful walk through how the kind of intricacies of how that works. So far, this is all sounding great. Clusters can scale up and down both in workload and compute resource, and scheduling is all working perfectly. But you'll quickly find when your workload scales down, it might not happen how you would anticipate it to, which can lead you to undesirably loaded clusters when what you would really like is for things to rebalance. So if we were to look at, say, our deployment spec, you'll notice that there's no field or instructions for Kubernetes on how you'd like your workload to be rebalanced. Put simply, once Kubernetes has scheduled your workload, it considers its job done. That's the end until something kind of goes wrong, fundamentally. So this has been an issue that's played on many people's minds, which has led to the desire for what we call descheduling workload in order to let the scheduler then readjust with new information. So I might be showing my age now, but I remember a time back in the days before when I used to have to defragment my hard disk. Hours and hours spent staring at a screen that looks something like this, because the way the system works is when data is written, it's written anywhere, and then when it's later deleted, that can leave some gaps. Not fundamentally dissimilar to how Kubernetes schedulers works. So when you delete workload, you can find yourself with gaps. If you were to reschedule everything from scratch, wouldn't really exist. So the effects of scheduling then causes our old friend, the Kubernetes scheduler, to notice that a pod has been deleted from an undesirable location and create a new pod. And then go through all of the process of filtering what nodes are available to run the workload with all sorts of complex rules, and then scoring them through some even more complex rules before deciding where best to place the workload. In order to do this, the descheduler has policies that you can define at a cluster level. These are split into two categories of balance and deschedule, where balance is intended to redistribute your workload across the nodes, and the deschedule is intended to cause the workload to be evicted based on some rules, such as the lifetime of the pod. And the configuration looks very familiar to other things in Kubernetes in that it closely resembles a CRD. Though, don't be fooled by this, it's not actually a CRD. You have to put this in a specifically named config map as a text blob. So in here we can define our plugin configurations in our profile and elect which plugins should be enabled. And our categories that we saw earlier are referred to as extension points. So there are other extension points available, but we'll be focusing on the deschedule and balance ones only today. A common use case that you might have is that you've got applications that for whatever reason you want to restart, maybe once an hour or once a night because reasons, refresh things, keep things clean, avoid collecting state. So an example of that configuration might look something like this, where we will look to restart pods that are over 10 seconds old. So this is the exciting point where I make my first prayer to the demo gods for the first time today. So to have a look at a cluster that we've got here. So I've got a 3-node cluster, which you can see I've illustrated on the right-hand side for this. If anyone's interested, the code for this is open source that's been put together, where it's actually talking to a real Kubernetes cluster that's running in Linode at the minute. So, and I can do kubectl get pods, and I can see that I've got 3 pods running. So what I'll start by doing is I've got some code here. So let's have a look at my restarting descheduler policy. So what we can see is I've got a descheduler policy, and I've defined a pod lifetime plugin with a maximum pod lifetime of 10 seconds. So as you can see, these pods have been running for a while now, 150 minutes each. So when I apply this, what we'll find is that it will that we'll start seeing kind of seconds in that time again. So let's go ahead and apply that policy. Cool. Now, I do have this running every minute, and we'll come to that in a minute. Oh, okay, cool. So we've happened to have landed at the right sort of time. So what we've seen here is that we've now kind of got an age where it now is 10 seconds. Now, what you'll inevitably find is that the descheduler is only running routinely. So whilst I've said 10 seconds, that is only going to be re-evaluated the next time the descheduler runs its process. And at the minute, it's configured on this environment to run once a minute, which is probably fine. But because I've said like in seconds, that does mean that whilst I've said 10 seconds, I'll probably get 60, because that's the next time it will be re-evaluated. For fun, let's force the descheduler to run another run, which I've just done. So what I've done is I've created a job. We'll look more at that in a little bit of actually how the descheduler is executing. But what I've done is I've just created another job off the back of the cron job that exists, and that's caused that descheduling to occur. Cool. And I could do that again, which would see that it should, if I manage to catch that in time. The second time I ran that, it didn't evaluate, didn't evict anything, because I did it under the 10 seconds. But if I run it again, over, then of course I'll see all my containers being terminated and recreated. Cool, that worked surprisingly well. So going back to my deck, so I've lost my notes, right. So there are a few more options for how you can run the descheduler in your cluster. You could run it as a one-off job, or perhaps you've got some other orchestration system in place that will create jobs on your cluster for you. Or a cron job, resulting in periodic jobs being created as you desire, as we just saw. Or you can run it as a deployment that will run as a process somewhere in your cluster in a loop at kind of regular intervals as you define. So let's have a look at the cron job option, which is what we just saw. So here we can see a cron job specification. This is going to execute every minute, which is the highest resolution that the Kubernetes cron job allows you to have. So depending on your size of cluster and shape of workload, this may be undesirable. You may want more or less frequent. Because it will run as a cron job, the descheduler pod will be created somewhere on your cluster, allocated dynamically, and of course will use some resources of its own and be a pod of its own right, which arguably could end up influencing the scheduler when it comes round to rescheduling all of that workload that it's just got in its list. So to having it disappear as soon as it's descheduled the workload can allow for the newly rebalanced scheduling to happen without the presence of the descheduler's influence kind of distorting reality. Another approach is to run the descheduler in a deployment. So it does support a highly available configuration where you can have multiple concurrent deschedulers running, and they will then periodically run to delete pods. However, only one descheduler is actually doing the work. They will elect a leader, and the other replicas will only become active if the current leader is unavailable. So to look at another policy that is available to you, there's the duplicate policy. So if we consider a scenario like this, if we were to lose the right-hand node, your orange pods would suffer a 67% impact, and your green nodes would be entirely unavailable until the node outage was picked up some 5 minutes later by the kubelet not reporting to the API server, which is what the remove duplicates balancer is intended to kind of address, which could cause your workloads then to rebalance across our nodes and reduce our concentration of a single node. Okay, demo gods again. So, right. So what I'm going to do is I'm going to, for the sake of simplicity, I'm going to have get the name of the first node. So that's the name of my first node, which I'm going to do some work with. So the first thing we need to do is obviously remove our restarting policy, because that's going to distort some things. So we'll do kubectl delete restart. What's it? Oh, it's 03. Restart. Cool. Okay. Cool. And now we are going to we'll drain the that node, which was this one ending. Where are we? EFE. Which one is that over there? Never mind. Okay, we'll figure that out in a minute. So we will. Okay. So what that's going to do is that should evict the nodes. Hopefully that's going to work. Oh, my thing on the right-hand side here doesn't appear to be refreshing. There we go. Okay, fine. The node on the right-hand side is not got anything on it. Sorry, my browser was not refreshing the page. Okay, so what we can see now is we've got one empty node up at the top, because I've drained that node, so there's no pods running on that at all. And I've got one node that's got 2 pods on it and one node that's got 1. Cool. So if I now if I remove the cordon, so this would be in effect, maybe let's go with the scenario. I've taken that node offline to do some maintenance on it. I do some things, right? So I've drained it, removed any workload from it, let everything end kind of cleanly. So that's now uncordoned that node. It's back online. Now, in theory, if any new workload were to be introduced to the cluster, that would go there. That's cool. But my existing workload that's now here, well, I've got quite an unbalanced cluster, this node maybe is this bottom right-hand node is maybe working quite hard. And the top node that I've got is just sitting kind of idle, dawdling. Depending on the kind of shape of your workload, that could run for quite a long time. So let's have a look at my duplicates policy. So what this one's going to do, very simply, it's going to deschedule pods if there's duplicates on the same node. In order to try and rebalance them. So this is part of the balance plugin rather than just descheduling. Cool. So let's apply that policy. Okay. Hopefully I've got that in time because we're about to see the minute hand go round, and we'll see if anyone's astutely watching on the right-hand side here, this middle kind of pane on my window. We can see when the descheduler operates, which is every minute. I'm impatient, so I'm going to force that to run. Oh no, it's gone. I didn't get to it in time. Okay, cool. Awesome. Again, worked exactly as I'd expect it to. So now what we can see, so I've got now a freshly rebalanced cluster. Happy days, right? So I can see that I've got a couple of pods that have been running for about 3 minutes and a fresh new one that's just been rescheduled that's now been running for 20 seconds on the node that I drained. Cool. Okay, great. So let's delete that policy so I don't forget it, and come back to the slides. So metrics are a pretty big deal in Kubernetes, as you're no doubt aware. So while there are more advanced metrics capabilities available, the descheduler uses some more primitive and consistently available ones. If we remember how the kubelet that exists on every node works, the job of the kubelet is to keep the current node synchronized with the state of the control plane. So it continually polls the control plane for updates. Remember when we said that the scheduler assigns pods to the nodes? Well, if the kubelet finds a pod assigned to the current node, it will retrieve the spec for that pod, causing the Docker image to be pulled down, given to container D, and start running. The kubelet then reports the ongoing health of the node and the pods to the kubelet, and it uses cAdvisor to gather local metrics on CPU, memory, and disk concentration to send off to Kubernetes, the Kubernetes API server, where that is then tracked. For the astute amongst you, cAdvisor is due to be replaced in the next release of Kubernetes, but the principle will remain the same. So using that data allows us to make some interesting decisions on how to deschedule our workloads to reach a more desirable balance. As an example of this, this is the high node utilization plugin, which will work to schedule your workloads to maximize your bang for buck on compute nodes. So if you have a node that's looking like this on the left, it will identify the underutilized node and deschedule the workload in order to allow your cluster to autoscaler to remove that node. As a quick refresher, when you provision, say, a compute instance of any sort, you might think that the memory and CPU are available and can be used by your running pods, and you are, on the whole, right. However, some memory and CPU should be saved for the operating system. And you should also reserve memory and CPU for the kubelet. Sorry, just seen Salmon asking me to make sure I zoom my terminal a bit more when I'm doing demos. Yeah, I'll sort that out the next time around. So, is the rest then made available to the pods? Well, not quite yet still. You might need to reserve some memory for the eviction threshold. So if the kubelet notices the memory usage is going over the threshold, it will then start evicting pods. Daniele, or of course D5E to his friends, did a brilliant talk on this last month, and the considerations on how to right size your cluster, which again, if you didn't see, please kind of do seek that out, seek that webinar out that we did last month. So next up is the low utilization policy, which provides a few more options to try and achieve a sweet spot of node utilization by providing an upper threshold and a lower threshold. So in my scenario, a node under 20% is considered underutilized and over 70% is overutilized, which will cause the descheduler to rebalance accordingly to try and get the nodes into that sweet spot between. Okay, last time of praying to the demo gods and with a zoomed in screen. So hopefully that's a bit better for you. The other ones are mostly for me, but you can obviously zoom in on them because it just makes me sure I can see that things are actually happening. Okay, so let's have a look. Right, so now I want to do is I've deleted the previous policy. So I'm going to drain my node again, which will cause that to then get descheduled from that one naturally because I've descheduled the I've drained the node. So no workload can go into this top node up here. I'm now going to scale my deployment up a bit. Now, the dashboard here is a bit broken. You'll have to bear with me. What you'll see is it will kind of do a bit like that. Actually, let's do like less than that, I think. Maybe. That's still going to be ugly. Okay, we'll stick with 12. You'll have to bear with me. There are 12 pods running. We can see a bit of distribution kind of here. It's not great, is it? But yeah, you'll have to believe me that there's, you can just about kind of see, should have put an outline on these boxes. But there's 6 obviously on these 2 nodes here. And this node up here is still completely empty. Okay, cool. So now we're going to uncordon our top node. And let's just look at what the policy that I'd like to apply is. So this, as I said, kind of with the slides, we've got a low node utilization policy where we've got a threshold of 20 and a target threshold of 70% of memory. And we've enabled that plugin. So let's apply the policy and try and get that in before the next minute clocks with the descheduler. Okay. Give it some time. And what we should see is that will, in effect, do roughly what we saw the balancer do kind of in terms of the workload. So we'll see this middle pane kind of scroll in a second. There you go. Cool. So we can see now we've got a node with, we've got one node, the bottom one's running 4 pods. This one's running 5, which you can kind of see in that there's this kind of funny one that's overlaying here, and the top one's running 3. So that's hit my kind of sweet spot where this middle node is running at 70%. And that's kind of where I wanted it to be. This one's lost, so it lost 1 of its pods. The bottom node lost 2 of its pods. And those 3 pods have kind of collated up onto this top node. So that this kind of gives us quite a dynamic kind of ability to say, well, I want to find a sweet spot for node utilization. Okay. All right. So back to the thing with the, oops. Right, sorry. Okay, so related to a lot of this space is the node problem detector. So there are fundamentally loads of things that can go wrong with a computer, as you're no doubt familiar, but or in this case with a node. But without this, without the node problem detector installed, Kubernetes will be totally unaware and will continue to schedule workload on an unhappy node until it's past the until it's marked offline some 5 minutes later by default, after it's totally failed and failed to check in with the kubelets failed to check in with the Kube API. So you can run this node problem detector as a daemon set in your cluster. So this means that it will run on every node and can detect things such as NTP, for example, network time protocols kind of thing being down. So the time on the server's out of sync, something that's probably quite important to most people. CPU, memory, and disk issues, perhaps, kernel deadlocks, corrupted file systems, issues with the container runtime, or indeed the kubelet, and report those to the Kubernetes control plane ahead of time. The node controller is the Kubernetes component that is ready to process the information. After it has arrived at the API server, the node controller lives as part of the controller manager and can add taints such as unreachable to the node. Combining this all together with the node problem detector deployed, if it detects that the node is unreachable, the node can then be tainted. And the taints violation policy, a feature of the descheduler, could be configured to reschedule the workload on a tainted node, causing the descheduler to evict all of the current pods, and then allow the scheduler to rebalance the workload. And this will prevent any pods being scheduled on the right-hand node. In combination with the cluster autoscaler, it can notice that the utilization is low and trigger the downscaling of that node too. So that was a pretty long journey. So some key takeaways. Vanilla Kubernetes will not rebalance or defrag your nodes and pods. The descheduler is a component that exists as an add-on that will take on this task. And it's configured by policies that dictate its behavior and will drive your cluster to a more desirable distributed configuration. It will take some low-level metrics from the nodes and pods in order to inform this, rather than using, say, the metric server or similar. And the node problems detector can be used to provide early reactions to nodes becoming unhealthy and direct your workload to run elsewhere. So thank you very much for your time. I'm Chris Nesbitt-Smith. As I said at the start, find me on LinkedIn, or be sure to check out the other webinars that we've done with Linode 2. Like and subscribe, whatever the kids do these days. So now I'll open the floor to questions. If we don't get to you, or you're not watching this in real time, then please do join the Slack community. So let's have a look. What have we got? Question 1, how does the descheduler complement the default scheduler in Kubernetes? Are there scenarios where these might conflict? So the Kubernetes descheduler is as a complement to the one that's built in. So it works by optimizing the distributions of pods across the cluster, which is something that the default cluster kind of won't handle post that initial pod placement. So once it's put something there, it's kind of checked out and it's done its job. There are, of course, scenarios, situations where maybe some race conditions possibly that would cause the descheduler's actions to be in conflict with the decisions made by the scheduler. So you could end up with things kind of continually kind of descheduling. So it might evict a pod that actually is then going to get placed there again. Entirely possible. Obviously, you can do some monitoring to kind of see how that works too. But it is possible, so you can tune your configuration to that end. So maybe you rebalance more selectively. Don't look for things under a certain time or something like that, perhaps. Cool. Any follow-ups to that, then please kind of do add them in, and I'll circle back around to it. Question 2, if you were to add a balance policy, but certain pods can't be scheduled on all nodes because of parameters like node select, taints tolerations, affinity, how does the descheduler respect those and avoid evicting those pods? So yeah, interesting one. So the descheduler will typically look at the taints and tolerations and take those into account. So it's trying to do a reasonable job of executing. So particularly in the rebalancing, it's only going to execute the rebalance if it can do. So what we saw this firsthand when we ran the thing, because when I was drained and that also created a cordon on the node, that was in effect just a taint on the node. So the drain just deletes all the pods, and it also will set a cordon on the node as well, which is just a taint that says that nothing can be scheduled here. So we actually saw that the descheduler in that process actually respecting that, because naturally it couldn't just unilaterally delete pods. There was nowhere for them to go, no resource to rebalance towards. Cool. Okay. What metrics and signs should we monitor to understand when it's beneficial to implement a descheduler? So if you look at if you look for your resource utilization, so look at how hot your compute is running, how much CPU and memory is being consumed. So if you've got, say, the metric server, that can give you a good idea. And particularly if you're auto-scaling your clusters, you might see a imbalance that accrues over time. So if you delete all of the pods over your entire cluster, probably wouldn't, but like if you did, then you could have that. You could then see that how that rebalanced, and then over time, you'd see a distortion and that fragmented effect appear. And that could be where you'd be able to look for that. And start to get an idea of how bad is the estate, and also then how do you tune the descheduler to minimize that and get you the most value for money, and avoid you having a large compute bill when you've got lots of nodes that are underutilized, particularly when you downscale. Cool. Good practical uses of the descheduler in production. Sorry, so the question is, have you seen any good practical usages of the descheduler in production? Can I give some examples? So yeah, absolutely. One of the best examples is that cost saving fundamentally. So we want to downschedule our resource that we may have scheduled up. So let's take a thing like Black Friday, for example. We've scheduled up, we've created a load of additional nodes in order to handle the workload. The workload's scaled back down, then the clusters would like to scale down, but you've got a ton of nodes all running one instance of a pod on. Therefore, the cluster autoscaler is not going to remove that node. So that's when the descheduling can come in to help you with that and manage that for you. How does the descheduler ensure it adheres to any set resource quotas or limits? So the descheduler doesn't directly enforce resource quotas or limits, but it operates within those constraints. So when it's looking to rebalance, it's going to anticipate what the scheduler would do. If you were to give it that pod spec, well, would it put it on that node again? If not, if that would cause a rebalance, then that's where it would be placed. So it doesn't enforce, but it does use that as a cue in terms of how it's going to balance the cluster out. It's not just number of pods, as we saw in our specifications. It was based on memory utilization, particularly on those examples. Question 6. So, can we use the cluster autoscaler Carpenter with descheduler? So, if you are in AWS, then Carpenter will basically do all the thing for you, which is a combined kind of cluster autoscaler and will also do your descheduling. So that's a good answer. If you're in that ecosystem already, then absolutely do look at Carpenter, but it is specifically AWS related. Question 7, if I use AWS Carpenter, how will it help? Again, it will do all of the work for you. However, it is AWS specific. Is it safe to use descheduler in combination with Carpenter autoscaler? Yeah, conceptually. I mean, if you stop Carpenter managing your managing like your actual pods and your workloads and optimizing that, then yes. But again, AWS only. Question 8, can pods that would be disruptive to deschedule be excluded from rebalancing based on labels, annotations, and so on? Yeah, so absolutely. There is a, you could potentially kind of label the pods with, say, descheduler ignore, or you could maybe ignore, define your rules based on prod priority. And there's also the pod disruption policy, which might be relevant to you to also consider too. And you can use that to inform your inform how you configured your descheduler. Can we create a descheduler policy in order to keep a good pod balance between nodes on different zones? So yeah, absolutely. You can use this with whilst it doesn't kind of have that awareness out the box per se, if you use kind of node affinity and anti-affinity based on the labels on the node, then you would totally be able to achieve that and cause the descheduler to do what the scheduler would do. Ideally, kind of when if you were to give it those pod specs again, like delete the deployment, recreate it, and it would, if you've defined that so that it will distribute across the zones, then the descheduler will work to try and get you the same thing given the right config. Would you provide recommendations when dynamically rebalancing workloads and optimizing resource utilization in Kubernetes? So when it comes to scenarios that might create issues if using GitOps tools like Argo, CD, or Flux. Would you provide recommendations when dynamically rebalancing workloads and optimizing resource utilization in Kubernetes when it comes to scenarios that might create issues if using GitOps like Argo and CD and Flux? I don't think recognized where that's necessarily going to cause an issue, no less than actually if you were to allow your cluster to get to a point of failure or a node failure or node being unavailable. Same thing is going to fundamentally occur, is that something if you're descheduling because of node concentration or node issues, then that node might fall over. If it was allowed to persist and carry on, then it might actually ultimately fail, in which case you'd be dealing with that problem anyway. So maybe if you could be more specific with kind of what sort of scenario particularly that you're kind of suggesting, but I don't, off the top of my head, I can't envisage a scenario where that should really occur, like in terms of a conflict when using that. It's not like it's not adjusting like the number of replicas at all. It's just deleting the pod, which will then cause the scheduler to go and recreate it elsewhere. And the same thing could happen through any other scenario. If you're worried about it, of course, you could just look at your cluster that is all managed by Argo or Flux and just go and delete a few pods, see what happens. If it all works, then the descheduler is going to be just as good, like a kubectl delete pod dash, and then pick a random pod. If nothing goes wrong, then the descheduler is not going to be doing fundamentally any different to that. Does descheduling use the amount of CPU used by the node or the amount of CPU defined in the pod's requests? Is it possible to configure descheduling to use the amount of CPU allocated to the pod during descheduling? Descheduling. So does descheduling use the amount of CPU used by the node or the amount of CPU defined in the pod's requests? Is it possible to configure descheduling to use the amount of CPU allocated to the pod during descheduling? So the descheduler uses the CPU memory requests that are specified in the pod specs for its decisions, not like the real-time usage of the pod per se. But it will use cAdvisor in order to understand the memory concentration on the node in order to rebalance, if that answers that question, or memory or CPU or disk pressure on the node. So it's using that to, depending which depending which policies you're utilizing, then it will take kind of a bunch of bits into account on both kind of the real-time consumption and the like what's available on the node. So you could obviously have a node perhaps that had some processes running on it that were nothing to do with Kubernetes, that had gone awry. Maybe some agent that's running on the machine, who knows, that's running on the node, and Kubernetes has no awareness of it. The cAdvisor process that I touched on earlier would still pick that up. Cool, which I think is all the questions that we've currently got, although I can see something. Yeah, that's all of them. Great. So if you do have any more questions, then please, or you're not watching this in sync, then please do kind of join the Linode Slack and kind of raise a kind of question in the, I think there's a Kubernetes-scaling channel in there, which is a great place to kind of talk about these problems. There's also the the Kubernetes scaling one. So yeah, please join that. And if you've got any more questions or thoughts that you'd like to share, then that'd be fantastic. Yeah, I guess that's great. So this is the last of our kind of 3 parts webinars that we've done this year. Hopefully you've enjoyed them and got some stuff out of them. So as I say, please do like, subscribe, share these recordings that will be kind of available in perpetuity. And you obviously will refer back to them. All of the code for all of this is all open source, which I hope I'll certainly share some links for in the Slack channel, which will give you a reason to join it, if nothing else, where you can see the code that I've been working with today and kind of replay the labs that I've been executing too. So finally, thank you very, very much for your time. It's been a pleasure to have you. And that's about it, I guess. Cool. Thanks a lot. Bye.